Hey everyone, today we're going to do a video on the unit circle, the sine, and the cosine functions and how they kind of relate and connect, okay? So to start things off, let's look at our unit circle on a typical Cartesian plane, on a typical graph. We have our x-axis and our y-axis. And so since it is, after all, called the unit circle, we know that the radius at any point on the circle is always a unit of 1. And so the radius here, and likewise the radius here is 1, okay? Now here's something that is really, really fundamental in understanding how a unit circle kind of relates to the sine and the cosine functions, okay? Now at any point on our unit circle, okay, so let's take some arbitrary point, let's say around here. The coordinates, let's say at some generic point P, any point that happens to fall on the unit circle itself, which is by definition, since it's on the unit circle, is 1 unit in distance away from the origin, right? Any such point P has coordinates instead of x and y, as we most commonly write the coordinates. We can write this as, if we designate theta to be the angle between what we call the terminal arm of our point, which is simply the line connecting the origin to our point P, let's call the origin O. If we have an arm that connects the origin to our point P, and we have the x-axis, and we designate the angle between these two lines to be called theta, then instead of simply having the coordinates as we've typically written them, x comma y, we can equivalently write the coordinates of this point on our unit circle as x becomes cosine of theta, again, theta being the angle between the arm connecting the origin to the point P and the positive x-axis, and the y-coordinate becomes sine of theta, okay? And you can see that by a geometrical argument that connects our point P down to the x-axis, okay? And I will show you how that works. Now, our y-coordinate, right, since we're starting on the positive x-axis, our y-coordinate is simply the vertical height of this line here, of the line that creates this nice right-angled triangle with point P on the top corner, okay? And so if this height is our y-coordinate of point P, I'll write that as y equals, then if we use our old grade 10 math trigonometry of SOHCAHTOA, I'll jot that down to refresh your memory in case it's gone away a little bit. We have angle theta in the bottom left corner. We know that the hypotenuse, right, the side opposite to the right angle, and always the longest side, the hypotenuse of this right angle triangle, we saw this in grade 8 for the first time, the hypotenuse is length 1. That's by definition. That's why we can always create such triangles, because any point that falls on the unit circle has a hypotenuse of 1 unit, okay? So we know the hypotenuse is 1. And from angle theta, the way it's shown here, this vertical side is the opposite side, right? And so now we're looking for the opposite side, and we know the length of the hypotenuse. And so that falls under, we know hypotenuse and we're looking for the opposite, and so we're dealing with the sine function, okay? And so that means that y is equal to, well, what's going to be equal to? Well, the sine of theta from our SOHCAHTOA argument is equal to the opposite over the hypotenuse. The opposite is exactly y, and so we'll have y over the hypotenuse, which is of length 1. And so sine of our theta is equal to y over 1. Okay? Now, we can rearrange this to have it in the form of y equals. Clearly, we can multiply both sides by 1, or we can simply notice that y divided by 1 is equal to y. And so what we really have here is the result. Sine theta is equal to y. And we don't have to go any further. This is how our y-coordinate becomes precisely sine theta. And this is true for any angle theta on our unit circle and for any point P on our unit circle, because there are absolutely no restrictions. There were no conditions on how we created this point P. There were no conditions on how we created theta. It was simply the angle that was constructed by connecting the origin to a generic point P that is on the unit circle, anywhere on the unit circle. And so this tells us for any points on the unit circle, the coordinates of said points are cos of theta, again, theta being the angle measured from the positive x-axis. So even if we go further, we simply start at the positive x-axis and we go from there. So the y-coordinate is sine theta, okay? Next, we have the x-coordinate. The x-coordinate is simply this horizontal side length down here, right? This is going to be our x-coordinate. Whatever this length is, that is the x-coordinate of our point P, right? That's the x-coordinate. And so now, based on the angle theta that is inscribed here, the bottom side is the adjacent side, right? The adjacent side based on SOHCAHTOA. So we're either going to be working with cosine or the tangent function. But we don't know the opposite side if we're looking at the adjacent side. What we do know is the hypotenuse. We always know the hypotenuse. It's precisely of length 1. Again, by definition, being on a unit circle. Unit means 1. And so if we're going to use the cosine function, because we're looking for the adjacent side, that's x. We know the hypotenuse, that's 1. And so C, cosine, tells us that cosine of angle theta is equal to adjacent over hypotenuse. So that's x over the hypotenuse being length 1, and so x over 1. And once again, we know that dividing anything by 1 really does nothing at all. And so we have the result that cos theta is equal to x. Okay? And there lies our second coordinate. X becomes cos of theta. Okay? And so what that means is that anytime you're being asked to construct a graph involving cos theta, sine theta, or anytime you're visualizing specific values of cos theta or sine theta, whenever you're dealing with calculus, with integration, with derivatives, with any kind of word problems, with related rates questions, anything that involves specific trigonometric values, this visual turns out to be really handy oftentimes, at least I found so, and a lot of my students think so as well. And so having this visual construct in your mind of how these values kind of run is very, very, very helpful. Now, since the y-coordinate is the sine of theta, then we can rotate theta through the entire circle, and since sine of theta is the y-coordinate, right, then we can see that as theta goes from 0 all the way through, you see the y-coordinate for any point that would go, we're just going to rotate our point along with theta. So if theta ends here, our point P would be up here. And if theta ends here, let's say, then our point P would be down here. Okay? Now notice that for theta starting at 0 all the way through to this is 180 degrees later, right? That's 1/2 of an entire circle's worth. That's 1/2 of a full revolution of a circle. And so 1/2 of a full 360 is clearly 180. This whole time, if you track this point P through from this positive x-axis, 1 unit away from the origin, through the top half of our unit circle, the y-coordinate is always positive, right? It's it starts at 0 and then becomes positive, 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 until it drops back down to 0 when we hit 180 degrees. Now, since y gives us precisely sine of theta, then there are many values that we can kind of embed in our minds, in our memories, that are easy to recover anytime we need them. So, for example, if the point P is right here, then theta is 0 degrees, right? It's smack dab on the x-axis. And so that means that sine of 0 is simply the y-coordinate of this point here. The y-coordinate of that point there is 0. And this tells us that sine of 0 is exactly 0. We get back to a y-coordinate of 0 when we're back on the other side. Again, right on the x-axis, and so the y-coordinate at this point here would also be 0. But here, theta is now 180 degrees. And so we also get the fact that sine of 180 degrees is equal to 0. And then if we kept going, if we did a full 360 rotation of theta, we would end up back at a full circle's worth of rotation, back at the point we started out with. And so we also get that sine of 360 degrees is equal to 0. Those are kind of the first points that we would look at memorizing to kind of lay the foundation of our understanding of the unit circle, which is so important for all of you that are studying calculus in university. Now, there are two more values that I'll just jot down quickly. I won't go too far into the details of the 30, 60, 120, 150, so on and so forth degrees, because those can be for a later video. For now, I just want to establish the foundations of the connection between the unit circle and the sine and cos functions. And so if we look at the point up here, the highest point on the unit circle, which is exactly when theta, again, theta starts at the x-axis, and so if it rotates up here, we're looking at a 90-degree angle, right, at a nice right angle. And so this point up here is when theta is equal to 90 degrees. And what would the y-coordinate of this point up here be? Well, we know exactly what it is, right? It's 1. The length of this arm, because it's on the unit circle, is precisely 1. And so that tells us that sine of 90 degrees is equal to 1. And then by a similar argument, if we kept going through 90, 180, and finally down to 270 degrees for theta, now our point P would be at the lowest point on the unit circle. And since it would be 1 radius length away from the origin, and it's on the unit circle, then we clearly know that this length would be 1, and it's in the negative y direction, and so we get that the sine of 270 degrees is negative 1. Sine of 270 degrees is equal to negative 1. Okay? And from there, that's where a lot of your, the foundation of your knowledge and your connections from the unit circle to the sine and cos values will come from, because you know that for any theta angle between 0 and 90 has to be between 0 and 1. Then any theta angle between 90 and 180 has to be between 1 and 0. And then between 0 and negative 1. And then finally between negative 1 and back up to 0. And that's how the sine values rotate around the unit circle, because the sine values correspond to the y-coordinate of the point P that's rotating around the unit circle. Okay? And this will correlate to a sine graph later on. If we want to draw a sine graph very quickly with only the really, really important points laid out, we'll have theta here, 270 degrees, 360 degrees, and we'll have y being sine theta, right? If we want to draw a sine graph, just a very, very basic sine graph for y is equal to sine theta, well, we can kind of run through these values. When theta is equal to 0, then the point is right here, because we're always starting in the positive x-axis. And so the y-coordinate for this point, the coordinates for this point, the coordinates for this point are 0 and 0. And so sine theta is equal to 0. That's why our sine functions always start at the origin before any transformations come in. So we start at the origin, then at 90 degrees, we're up to a y-coordinate of 1, right? Sine of 90 is equal to 1, and so at 90 degrees, we have a y value of 1. At 180, we're back down to a y-coordinate of 0. So this point here is at -1 in x and 0 in y. Excuse me, this point is not at 0, 0. It is at positive 1, 0, because that's 1 unit away from the origin in the x direction. Excuse me for that. So 1 and 0, -1 and 0. So sine of 180 is equal to 0. So at 180 degrees, sine of theta is back at 0. At 270, we're down here at the very bottom of our unit circle. And so that's a y-coordinate of -1, right? The coordinates at this point would be 0, -1, and so -1 being sine theta means that we have a point down here. And then finally, at 360 degrees, that's an entire circle's worth of rotation. We're back at our starting point, and so our y-coordinate is 0, sine theta is 0, and so we're back on the x-axis, or the theta axis in this case. And you can start to see our sine graph. That's not going to work very well. You can start to see our sine graph taking shape. And you can see how this sine function graph continues forwards and backwards in the same fashion that the y-coordinate, which is sine theta, can continue as we rotate through the unit circle once. That's 1 revolution, and 2 revolutions, and 3 revolutions, and we can keep going however many times we would like, up to infinity if we had to, and that's why our graph of our sine function can continue in a similar fashion, forwards and backwards, because we could also rotate clockwise rather than counterclockwise. Again, however many times we would like, and so if we went backwards, it would look similar, but going into the negative direction, okay? So again, I really hope this helps build just a very, very fundamental layer of understanding of the unit circle and how it connects to the sine. And then the cos function, we'll do another video on it later, but it would be very, very similar, almost symmetrical, but with the x coordinate. So cos theta, likewise, connects to the x coordinate of our point. And so the x coordinate, as we go through the rotations of our unit circle, would act in a very similar but slightly different fashion. And so again, I really hope this helps build some connections between these concepts that can be a little arbitrary in nature and tricky to wrap our heads around. Please let me know if you guys have any questions, comments, suggestions, and again, any requests for future videos, always appreciated. Thanks for watching.